So now we're going to talk about limiting reactants. And so we're going to go back to the pizza example. And there's our recipe: 1 crust, 5 ounces of sauce, 2 cups of cheese makes 1 pizza. So now we're going to look at not just what if we had 10 cups of cheese, but what if we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce? How many pizzas can we make? So I'm giving you some time to think here, because this is like a real life sort of problem that we can all think about, right? So how do we even approach this problem? Well, dimensional analysis would be awesome, but just regular people. Yeah, so we look at each ingredient and see how many pizzas can that make, right? And so we figure that out just thinking about it, but what you're doing in your head is more like this. If I have 4 crusts, I can get 1 pizza for every crust, right? So that's 4 pizzas. And I've got 15 ounces of sauce. And I get 1 pizza for 5 ounces. So that's how many pizzas? 3 pizzas. And the 10 cups of cheese, 1 pizza takes 2 cups of cheese. So that would make 5 pizzas. So I can make 4 plus 3 plus 5 pizzas, right? No, that's silly. I can only make 3 pizzas, right? Because when I make 3 pizzas, I run out of sauce, and then I can't make any more pizzas. They're like working for some really just rigid boss, and they're not going to let you be creative and put ketchup on it or something. Right? It's just like, no, you run out of sauce, you're done. So 3 pizzas.
You can make cheesy bread too.
You could make cheesy bread. Yeah, you could do some other things, but you can't make pizza according to the rigid recipe, right? So everybody okay with that? That makes sense, right? This is the same thing that happens with chemicals. The ingredients are the reactants, and you have to have the right amount of each to make the product. And when you run out of one of the ingredients, you can't make any more product. So what happens to the extra crusts and cheese? They sit there, right? They're still there. When you're done making pizza, they are left over, right? Okay, so there it is in pictures, because, pictures are nice. So 4 crusts, 4 pizzas, 10 cups of cheese, 5 pizzas, 15 ounces of sauce, 3 pizzas. So we figured out how much product we could make from each of the ingredients, and then we look at which one produces the smallest amount. And this is the answer. Now, so we call the tomato sauce the limiting reactant, limiting reagent. It would be the limiting ingredient, talking about food. And that's the reactant that makes the least amount of product. It's the one that we run out of that limits production, right? So it's the limiting reactant.
It's the one that's run out first?
Yes, it's the one that runs out first. Because once you run out of that, production stops, right? So that limits your product. It's the limiting reactant. It's the reactant that limits production. When we look at the 3 pizzas, that's called the theoretical yield. Because when you set out to make 3 pizzas, do you always make 3 pizzas? No, sometimes things happen, right? You got distracted by YouTube cat videos and you didn't hear the timer and you burned one, right? So you have to throw that one away. Or the cat jumped up on the counter and ate all the pepperoni off of it or something. Yeah, well, there's no pepperoni on this. Ate the cheese, right? messed it up. There's all kinds of things that could happen to screw it up. So we call this a theoretical yield because it's if everything works how it's supposed to. So the theoretical yield, the amount of product that we can get based on the amount of the limiting reactant. Okay, any questions? So in a chemical reaction, just like when you're cooking at home, it's very likely that one of the reactants is going to run out. If you set out to make pizzas, it's very unlikely that you're going to have exactly the right ratio of cheese and crust and sauce, right? You think about making cookies or something, and you're probably going to run out of something like eggs before you run out of sugar or flour. You're never going to have just the right amount of everything, right? That just doesn't happen. It doesn't happen in chemical reactions either. So when that one reactant gets used up, the reaction stops, just like pizza making. No more sauce, no more pizzas. So we call that the limiting reactant. The limiting reactant gets completely consumed, and the other reactants are left over. They are in excess. They are the excess reactants. We have more than what we need. And they just sit around afterwards. They're still there. Any questions? So, how much you actually make is the actual yield, right? So maybe you burn a pizza, you drop one on the floor, and so we only made 2 pizzas. We should have been able to make 3, but we screwed one up, something happened, and so the actual yield is 2 pizzas instead of 3. Things like that happen, right? So to express the relative success of this process, we use percent yield. You may be noticing we use percents a lot, right? And percent, again, is the part over the whole. It's the part we're interested in divided by the whole thing. So in this context, the part is our actual yield. How many pizzas did we actually make? And the whole is the theoretical yield. Out of how many could we possibly have made? And then we multiply by 100 to get a percentage. Okay, that's a percent yield. So this is a nice summary slide which gives a short definition of all of these terms. The limiting reactant, the reactant in excess, the theoretical yield, the actual yield, and the equation for percent yield. Okay, and these are all on Canvas, so you can go take screenshots of them there later if you need to. So let's apply these ideas to chemical reactions. So we were looking at the combustion of methane, and here we have our balanced chemical equation. 1 methane molecule reacts with 2 oxygen molecules to make these products. So 1 molecule of methane reacts with 2 molecules of oxygen. If we only have 1 molecule of oxygen, we can't make anything. It's like if you have 1 cup of cheese, you can't even make 1 pizza, right? There's just not enough. What if we had 5 molecules of methane and 8 molecules of oxygen? Well, we're going to apply the same thought process as we did with the pizzas. We're going to look at each of the reactants and figure out how much product could we make. Now this time there are 2 products, and they are related to each other, and so we don't have to look at both of them. We just look at one. And so we choose the one we're more interested in. Here we're talking about global warming and carbon dioxide, and so we're looking at how much carbon dioxide is produced. So if I have 5 methane molecules, for every methane molecule, I get 1 CO2 molecule. Just like for every crust, I can make 1 pizza. And so if I was able to use all 5 of these methane molecules, I'd get 5 carbon dioxide molecules. Okay? And then we look at the other one. The other reactant was the oxygen. And they said, well, we've got 8 molecules of oxygen. We get 1 CO2 for every 2 oxygens. And so from the 8, we can only make 4 carbon dioxide molecules. It's a little bit like the pizzas and the cheese, right? You get 1 pizza for 2 cups of cheese. Here we get 1 CO2 for 2 oxygen molecules. So the oxygen could make 4, and the methane can make 5. So what's going to happen? The oxygen will be the limiting reactant, because when we make the 4 molecules of CO2, we will have used up all the oxygens. There's more methane sitting there, but we can't make any more CO2 because we ran out of oxygen. Okay? We ran out of sauce, we can't make any more pizzas. Does that make sense? So we find how much product can be made from each reactant, and then we're looking for which one is the smallest amount. That's the theoretical yield. Because at that point, one of the reactants has run out, and so production stops. So let's look at this conceptual connection. Nitrogen and hydrogen gas react to form ammonia according to this reaction. So we need 1 nitrogen and 3 hydrogens in order to make 2 ammonia molecules. So a flask contains a mixture of reactants represented by the image shown on the left. Which of the following images best represents the mixture in the flask after the reactants have reacted as completely as possible? And what's the limiting reactant and which is in excess? Well, how about if we group these things together, right? It takes 1 nitrogen and 2 hydrogens. So if these guys got together, we'd make an ammonia, right? And then if the nitrogen here and 2 hydrogens, that would make another one. So what's going to be left? Some hydrogen. What gets used up? All the nitrogen. So which flask represents what's going to be there afterwards? Okay, see, I did it wrong. Look at that. Okay. I just did this to see if you're awake. No, I didn't. I screwed up. It's not 1 to 2, it's 1 to 3. And that's why none of the pictures worked out. Okay, 1 nitrogen and 3. See this number 3? I don't know. It's Monday. And a nitrogen and that's 2 again. God. 1, 2, 3. I'm learning how to count today. Okay, that's better. Now which one matches up? C. Okay. Phew. Shouldn't have been that hard. That makes sense? So what's the limiting reactant? Nitrogen. So nitrogen is the limiting reactant, and we get tired of writing these things over and over again, so I often just LR. And then what's in excess? The hydrogen. So hydrogen in excess. It doesn't matter how much more hydrogen there would be, we couldn't make any more ammonia because we ran out of the nitrogen. So any questions about this? It's really important to understand this concept using the pictures, because now we're going to do calculations with numbers, and if we don't have the picture in our head, then the numbers get really confusing. Okay, so this is the approach that the book gives, and it's a perfectly valid approach. There's nothing wrong with it. And if you like this and it makes sense to you, go for it. but I'm also going to show you the way I prefer to think about it. So when we've got masses of reactants, then we have to calculate moles, because the chemical reaction gives us relationships between moles, and we have to do the moles. So if we have two reactants, this example would be magnesium and oxygen reacting to form magnesium oxide. We take the grams of magnesium, we calculate the moles of magnesium and the moles of product. You take the grams of oxygen to moles of product, and then you decide which one's smaller. You take that answer and you go on to figure out the mass of the product. So that works. What I prefer to do is, instead of doing that thought process in the middle, I think it's just a very little bit of extra work to just go ahead and go all the way to grams of product. And the smallest is the answer. So this way you just do two extremely similar calculations. You end up with the mass of product for both. You pick the smaller one, that's your theoretical yield. Okay? So that's the approach I'm going to be teaching you, but if you like the book's method, you can do that. It's perfectly fine. Mm-hmm.
So if you compare the moles of the product and find the smallest one, would that still work?
Yes.
That does still work.
It does still work. So if you calculate moles of product and then you say, okay, well this, whichever one is smaller, I'm going to take the smaller one and then convert to grams.
So just the smaller one then?
Yeah, you ignore the larger one. But the way we're setting these things up, we go grams to moles to grams all in one calculation, right? And so this is causing you to stop in the middle and calculate moles and then to continue on and do grams. And I just think that's just not the best. It works. It definitely works. But I think it's more straightforward to just do two calculations and pick the smaller, right? Because the last term, as we'll see, this last term is the same molar mass for both. It's not like you have to calculate an additional thing. You just stick it on there and multiply. So it's actually really not that much more. Let's make sure I've got the right slide here. Okay, so here's a real example with the magnesium and the oxygen. Reaction mixture contains 42.5 grams of magnesium and 33.8 grams of oxygen. What's the limiting reactant? And the theoretical yield. And then it says, suppose that the actual yield is 55.9 grams, what's the percent yield? Okay, so lots and lots of questions there. Let's just start at the beginning. And so the first thing we're going to do is take the numbers out and write them under the balanced chemical equation. So it tells me I have 42.5 grams of magnesium. And I have 33.8 grams of oxygen. And it says I have 55.9 grams of magnesium oxide. So we put the numbers in and we're like, but wait a minute, there's no question mark. We've got numbers for everything. This is the actual yield. And the word actual usually shows up in there. Suppose that the actual yield is 55.9 grams, or 55.9 grams of magnesium oxide are actually produced, right? That is something that we have to give you because you have no way of predicting how many pizzas fell on the floor, right? So we have to give you that information, and typically it's given as we just say, well, we actually made one pizza, figure it out now. So this actual yield, we actually want to set aside. Oh, you're not going to let me do that? There it is. I like that. Just set it aside. It says, what is the limiting reactant and theoretical yield? Well, this is the product, right? There's only one product. And so it's asking, what's the theoretical yield? What's the most we could make if everything works perfectly? Okay. The clue that this is a limiting reactant problem is I have masses for both reactants. Not all problems will be limiting reactant, thank goodness, because these are just more work, right? But if you have 2 masses or 3 masses, you have got masses of all the reactants, it's a limiting reactant problem. I've got 2 reactants and a mass for each. That means I'm going to do 2 calculations. So I'm going to go grams to moles to moles to grams for the magnesium, and then I'm going to go grams to moles to moles to grams for the oxygen. 2 calculations. They're each going to give me a massive product, and then I just pick the smaller one, and that's my theoretical yield. Okay, so for the magnesium, 42.5 grams of magnesium, grams to moles. So I'm going to go to moles of magnesium, to moles. This is moles of the product. So moles of MgO. We're going to keep going. So you're just going to do grams to moles to moles to grams. And then we're going to go to grams. I've tried different ways of teaching this because I've been doing this for a really long time. And there are definitely times when we need to think about things, right? But when we think about stuff, we can get it backwards and turned around, and sometimes we forget steps. And so my general approach is, how can we do this with the least amount of thinking, right? And so if we just always do grams to moles to moles to grams, grams to moles to moles to grams, there's less thinking involved. And so I think that's better. So grams to moles to moles to grams for the magnesium, we're completely ignoring the oxygen. And then I put the units in here, grams of magnesium, and moles of magnesium, and moles of magnesium oxide. And these units are going to cancel out. And these stoichiometry calculations are why I feel it's really, really important to learn dimensional analysis. Because it makes these calculations very, very straightforward. There are other ways you can do it, but it just, again, way too much thinking. So now we put the numbers in. The mole ratio, mole to mole in the middle, comes from the coefficients of the balanced chemical equation. In front of the Mg is a 2, and so in front of moles of Mg I write 2. In front of MgO is a 2, and so I write 2 there. The first term and the last term are molar masses. The first one here is a metal, 24.31. And so it's an element, and so we don't have to do any calculating. We just pick it off the periodic table. And then that last one, we need to calculate. So maybe I'll do that up here. 24.31 plus 16. What's that? 40.31?
I'm just trying to find 1 mole, the weight of 1 mole, or 2 moles.
We're trying to find the weight of 1 mole for the molar mass. The 2 comes in here. So the last term here, this molar mass is always for 1 mole, and this is always for 1 mole. Double check my math. Yeah, 40.31. Pardon me? Because the 2 is in here. Okay, the 2's in there. We are using the 2. We have to use the 2's, but they're in here. And so if we start doing 2 moles out here and 2 moles over there, things get backwards really fast.
Just cancel out.
And it's not a good idea. It's more work, and you might do it wrong. So this is the same thing we've done before, grams to moles to moles to grams. These coefficients, the 2's, only show up in the mole ratios. A molar mass is the mass of 1 mole. Okay? It's a good question. I'm glad you brought it up. So now I can calculate how much product could be made from 42.5 grams of magnesium. So I'm getting 70.47. I'm thinking, well, how many of these digits do I need to write down? My starting number had 3 sig figs. So I'm going to keep 3 sig figs and write down 2 extras grams of magnesium oxide. I'm not done with the problem, so I'm not going to bother rounding it yet. So that's one possible answer. And then I'm going to look at the other ingredient and see, well, how much product could that one make? And you can't eyeball these. You say, well, there's less of this. It's less mass. Well, yes, it is. But these are masses, and these are ratios of moles, of molecules, and oxygen molecules and magnesium atoms, way different amounts. And then you also have the coefficients in there, and it's just not even worth thinking about. Just do the calculation. It's a lot faster. So we'll just do another calculation. So 33.8. Yeah, it's the janitor. He's sweeping the cobwebs off the window during my lecture. Because couldn't do that like before class starts. Brush, brush, brush. I'm not distracting at all. You could put up the screen and make faces at him. That probably would be nice. It's not a good idea to tick off the custodian. Where are we? Grams to moles to moles to grams. So grams of magnesium to moles of It's oxygen. Yes, thank you. Janitor. I'll blame the janitor for that one. Oxygen. Cobwebs, you can come sweep my brain. Might be good. Oxygen, 33.8 grams of oxygen. To moles of oxygen. To moles of what? The product, MgO. So when we did the pizzas, we took the cheese and we figured out how many pizzas, the sauce, how many pizzas, the crust, how many pizzas. We didn't take the sauce and figure out how many crusts do we need. We're just looking at the same thing, the pizzas. Yes?
The grams, would it be 15.999 or 15.999 times 2? Would you multiply by 2 for O2?
For O2, yes. Mm-hmm. Moles of magnesium to oxide, 2 grams of magnesium oxide. And moles of MgO, so the units cancel. Moles of O2, so the units cancel. Grams of O2. The mole ratio in the middle, moles to moles, comes from the coefficients. In front of O2, there's nothing. That means 1. And in front of MgO, there's 2. Here, this is the molar mass of O2. In the formula, there's a 2. It's 2 atoms together is 1 molecule. And so the molar mass for that is 2 times 16.0. So 32 grams. That doesn't have anything to do with the coefficients. That's the subscript in the chemical formula. So, in a separate problem, if I ask, what's the molar mass of O2? Well, it's 2 times the mass of oxygen, right? So that's 1 mole of O2 weighs 32 grams. And then this last one is the exact same term as the other one. So there's no thinking or anything. We just copy it down. And that's why I'm like, why stop there? Just keep going, and then you have the answer. So this is also 40.31 grams per 1 mole. So 33.8 grams divided by 32 times 2 times 40.31. And again, 3 sig figs, 81.154 grams of magnesium oxide. So even though we had a smaller mass of oxygen, that would make a larger mass of magnesium oxide. So how much magnesium oxide can we actually make? The 70. So you pick the smaller one just like we did for the pizzas. So the smaller one gives us our theoretical yield. I call that TY, T-Y, theoretical yield equals 70.5 grams of magnesium oxide. So that's one of the questions. What is the limiting reactant? It's the one that got used up. It's the one that gave us the theoretical yield. So whichever one gives us the smaller, you just look back over here, that's the limiting reactant. That's the limiting reactant, because that's the one that gets used up. There is more oxygen. If we put more magnesium in, we could continue up to 85 grams, but we ran out of magnesium, it's the limiting reactant. Okay, so we got that first. What is the limiting reactant and theoretical yield? Magnesium, 70.5 grams of magnesium oxide. Suppose that the actual yield is 55.9. What's the percent yield? Well, now I don't have enough space, so I will have to make some space. There. Space. Percent yield is an equation. So the percent yield is the part that we're interested in, how much actually got made. It's the actual yield divided by the maximum possible, which is the theoretical yield, times 100. So the actual yield is given to me. It's 55.9 grams. The theoretical yield I calculated, it's best to not use the rounded version in this calculation, 70.472 grams, and then multiply by 100. 55.9 divided by 70.472 times 100. And 79.322%. As both of those numbers have 3 significant figures, and so 79.3% is my yield. Yes? The theoretical will always come from the limiting reactant, yes. No, we'll never use this mass from the excess reactant because we can't make that much. Any other questions? If you have a hard time remembering which goes on top and which goes on the bottom, there's extremely rare circumstances where the problem might try to mess with you. Almost always, it's the smaller number on top and the larger number on the bottom. Because you cannot have a true percent yield that's over 100%. It means that something is wrong because you can't create matter. Yes? You need to memorize this one. Yeah. And if you remember, percent is part over the whole. Percent yield, okay, well, I need to do something with yields. I've got an actual yield and a theoretical yield. The part is the smaller, the whole is the bigger. Divide them that way. Yeah?
You want to round it to the nearest whole number, like 79%.
No. I don't want to round it to the nearest whole number.
What exactly?
I want to express my answer so that it expresses the uncertainty in the original measurements. Okay? So this 0.3 is, there's uncertainty there, it's estimated, but the 9 is certain. And so I know that this is, probably 79.2 to 79.4%. This isn't 78 to 80%. That's a much bigger spread. And so the goal of significant figures is so that our calculations tell us how precisely this can be known. Like when we are calculating, the grams of carbon dioxide emitted by burning all those barrels of petroleum, it came down to 2 sig figs, right? Now, your calculator is going to show you a whole bunch more. But there were so many estimations in that calculation that it's not reasonable to say that you know it to all these different places, right? Because it's just actually a ballpark number. And so following the rules of significant figures, we'll get an answer that reflects our knowledge of the precision. Any other questions? So magnesium, 70.5 grams, 79.3%. Those are the answers to the questions in that problem. Let's do another one. Ammonia can be synthesized by this reaction. What's the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? So I read the problem and I pull out the numbers and I write them under the equation. So hydrogen, it says 5.22 kilograms and 31.5 kilograms of nitrogen. And what are we trying to find? Theoretical yield of ammonia in kilograms. So we did a kilogram problem last week. And I showed you a couple different ways to deal with the kilograms. Does anybody have a preference?
Let's just convert our grams on the periodic table to kilograms.
We could do that. Just ignore it. So if I want to use kilograms with the periodic table, then I'm also going to have kilomoles.
No,
that's true.
But just let me show you this, right? So if I have 1 mole, you can put kilo in front of anything. Just like you can put mega in front of it. You say this celebrity makes mega bucks. Mega means a million. Millions of dollars, right? That's a metric system in popular culture. Oh no. So what's the molar mass in grams of hydrogen? 2 times 1.008, right? 2.016 grams. Grams of hydrogen. So 1 mole of hydrogen is equal to 2 grams. All of our conversion factors, the top has to equal the bottom. If I put a kilo on the top and a kilo on the bottom, does that change anything? Not really. Because those would cancel out. But I'm not going to cancel them out because I wanted them there. So that's another way to deal with the kilo. And when we get into solution stoichiometry, we'll find, especially with titrations and stuff, that millimoles are very useful because we get a lot of milliliters. Anyway, so there's that, but that's an entirely new one. So I've got 1 vote for ignore the kilogram. Should we go with that one? So we'll use the ignore the kilogram method. I just named it that. So we have 2 reactants with masses, and we have a product. So we're going to do 2 calculations: grams to moles to moles to grams, grams to moles to moles to grams. Pick the smaller. Okay. So I like to do the first one first. So we'll just start with the hydrogen. Yeah, that's what that is. Okay. And there's the kilo, and I put it in red because we're going to ignore it. I'm just going to leave it sitting there and go grams to moles to grams. So this is hydrogen, and I'm going to moles of hydrogen, and then what? Moles of the product, NH3. And grams of NH3. Grams to moles to grams. And then I put the units in. So those cancel out. And those cancel out. And grams of H2. And that's going to cancel grams of H2. It's not going to cancel the kilo. We're ignoring that. It's just going to sit there. So 1 mole of hydrogen is 2.016 grams, 2 times the mass. And then in the middle, I have mole ratios. In front of H2, there's a 3. So I put a 3 in front of H2. And in front of NH3 is a 2, so I put that there. The mole ratio is the only place I use the coefficients. Only place. And then over here, molar mass, I need the mass of 1 mole of ammonia. So that's 14.01 plus 3 times the mass of hydrogen. So 17.034. So 5.22 divided by 2.016 times 2 divided by 3 times 17.034. And I should have 3 significant figures. So I'm getting 29.403 grams of ammonia. And I'm going to bring that K over. Because I didn't cancel this out, I set it aside, I ignored it. It's still there, and I'm just going to bring it back here. Now what do I need to do? I need to take the nitrogen and do a very similar calculation. So 31.5 kilograms. Do the same thing, ignoring the kilo. Kilograms of nitrogen. Grams to moles to grams. We're going to the same destination. We're going to grams of NH3. So grams to moles to moles to grams. And moles down here, so those cancel. And moles of N2 down here, so those cancel. And grams of N2, and that cancels just the grams of N2, not the kilo. So for N2, it's 2 times the mass of nitrogen. So that's 28.02 is the mass of 1 mole of N2. In the middle, we have mole ratio. In front of nitrogen is a 1, an unwritten 1. So I'm going to write 1 in front of there. And in front of the ammonia is a 2. And then the last term is the same as the one above, so I just copy that down. $31.5 divided by 28.02 times 2 times 17.034. This should also have 3 significant figures. 38.299 grams of ammonia. But there's the kilo that didn't cancel up. Yeah?
There's no way we can find actual yield unless we either do the experiment or it's given, right?
Yeah, the only way to find the actual yield would be to do the experiment and measure it, to have them tell you what it is, or if they told you what the percent yield was, you could apply that to the theoretical yield and calculate the actual yield. But here we can't. We don't have enough information. Yeah. Okay, so what's my theoretical yield? 29 or 38? 29. It's the smaller, right? This is the smaller one. That's the theoretical yield. I'm going to go ahead and round that and give my answer as 29.4 kilograms of ammonia. Now, they didn't ask this, but what's the limiting reactant? Hydrogen. Whichever gives you this smaller number, go back here, and that's your limiting reactant. That's what you run out of. Any questions? $29.4 kilograms. Here's another one. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams Fe, determining the limiting reactant, theoretical yield, and percent yield. So let's take those numbers and write them under the balanced chemical equation. So 167 grams of Fe2O3, 85.8 grams of CO, produces that many grams of iron. What is the 72.3 grams? Am I going to use that in my calculation of the actual yield? Or, I mean, the percent yield? Or sorry. Yes. Yeah, I am. Okay, back that up. Rewind. Am I going to use this in the calculation of the theoretical yield? No. This is the actual yield. So we recognize this is the actual yield. I do need that for my percent yield calculation, but it's not going to come into my stoichiometry calculation. Now this reaction gives us 2 products. Do we care about the CO2? In this context, no, we absolutely do not. This is a mining company. They're taking this ore and they're trying to get iron out of it so they can build stuff, right? So they just care about the iron. This is a byproduct, goes off in the atmosphere. Maybe it's the mining companies that are doing the global warming. Probably not. They're making CO2. So what am I trying to find here? Grams of iron. So this is what I'm going for, grams of iron. This is just like an aside. It's there, but we don't need to think about it. So I have 2 reactants. I have a mass of each. I'm going to do 2 calculations. Grams to moles to moles to grams. Grams to moles to moles to grams. Pick the smaller answer. So 167 grams of Fe2O3 times, I'm going to go to moles, grams to moles, and then to moles of what I'm trying to find, moles of Fe, and then to grams of Fe. All the units in place. Then I can put in the numbers. So that first term is a molar mass. I need the molar mass of Fe2O3. So 2 times the mass of iron plus 3 times the mass of oxygen. $159.7. So 1 mole of Fe2O3, 159.7 grams. What should I write in front of moles of Fe? 2, because there's a 2 up here. And what goes in front of moles of Fe2O3? A 1. There is no number written here, so we understand that to be a 1. And then at the end, I'm calculating the mass of an element, so that's easy. I just pull the number off the periodic table. 55.85 grams of iron is 1 mole of iron. So 167 divided by 159.7 times 2 times 55.85. The book is really predictable in some ways. They almost always give you 3 significant figures. So if you have trouble with sig figs, try just round things to 3 sig figs at the end. That's probably good. 3 or 4, almost always. Okay. Then I do another calculation for the other reactant. So I'm starting with 85.8 grams of carbon monoxide. And I'm going to go to moles of carbon monoxide and moles of iron and grams of iron. Moles of iron down here, moles of CO down there, and grams of CO down there. What's the molar mass of carbon monoxide? I don't know, I'm going to calculate it. Carbon plus oxygen. Looks like 28.01. Two moles of iron. 2 moles of iron comes from 3 moles of CO. And then that last term, the same as the one above it, because we're going to the same place. 85.8 divided by 28.01 times 2 divided by 3 times 55.85 equals. Which answer is smaller, 116 or 114? 114, okay? So this is the smaller one. That's giving me my theoretical yield. So the theoretical yield is an answer, so I would round that and say 114 grams of iron. What's the limiting reactant? This is the smaller one. Go back here. There's my limiting reactant. This doesn't happen on a multiple choice test, but on worksheets or on post-lab questions where you have to do a calculation like this. Sometimes what I'll see is students will do this calculation and they'll do this calculation and it's just all beautiful and everything, but I have to take points off because they don't give me an answer. You have to choose an answer and you have to specify somehow. And I'm not going to be super formal, but like circle and an arrow or something. Just say, hey, this is it. Identify, okay? Because that's kind of an adult life skill thing, is being able to actually answer the question, not just spout off stuff. Okay, so what's the percent yield? So we have to calculate that, right? The percent yield is going to be the actual yield, which they gave us, 72.3 grams, divided by the theoretical yield, which we calculated, times 100. So 72.3 divided by 114.05 times 100. So 63.4% yields. Yeah.
Would there be problems staying around in the future where we wouldn't have the theoretical yield and we'll have to find instead the actual yield?
That's possible, yeah. So there are three things in that percent yield problem. You have percent yield, you have actual yield, you have theoretical yield. If you have two of those, or the means to calculate two of them, you should be able to calculate the missing one. Yeah. So can you see why a mining company might be interested in the percent yield for their reaction? Right? Yeah, because they're only getting 63.4% of the iron out of this ore. And so they're going to say, well, what can we do to increase this? And there are a lot of things that you can do to increase the yield. That's not a topic for today.
What is it called? What is this reaction called?
I don't know what this is. It's not fracking. That has to do with underground water stuff.
I'm not expert.
Yeah, I don't know. I don't know what it's called.
Carbon monoxide.
It's using carbon monoxide. Anybody else? So carbon monoxide 114, 63.4%.